Hi, my name is Elaine Corbett and I'm a Research Fellow at the Trinity College Institute of Neuroscience and School of Psychology in Trinity College, Dublin. This talk is about EEG signatures of decision formation in motion direction estimation. Cognitive models of perceptual decision processes that jointly characterize response times and accuracy, like the diffusion decision model shown here, have been hugely important in recent years in helping us to interpret the neurophysiology of perceptual decision-making. Neural signals recorded from humans and other animals have been shown to trace the evolution of decision processes over time, for example, like here in human EEG. But most of this work has used tasks with two or a small number of alternative outcomes, and therefore miss some of the complexity of many of our everyday perceptual decisions that have a continuum of potential outcomes. One example of this is that in continuous outcome tasks, strong biases towards certain categories of response are often found. So in color memory tasks, people are biased towards nameable colors, while in memory for motion direction, we find idiosyncratic person-specific directional biases. A recently developed model can characterize continuous outcome decision processes in a psychologically meaningful way by jointly accounting for response times and accuracy, which is in this case a continuous precision variable. In the circular diffusion model, the decision variable starts in the center of a disk and accumulates noisy evidence in 2 dimensions until the bounding circle is hit. Categorical biases, then, towards preferred stimulus directions can be accounted for by influencing the drift rate of the process, so the direction and rate at which evidence accumulates. We ran a continuous outcome version of the random-dot-motion task where people used a joystick to report their estimated direction of coherent motion of the dots from the full 360 degrees. We recorded 2 EEG signatures of decision formation. We generated a sensory level signal by oscillating the coherence on and off 15 times per second, and then isolating the 15 Hz signal in the EEG representing the coherent motion. We also recorded the centroparietal positivity, or CPP, thought to reflect the evidence accumulation process. We located the sensory level SSVMEP signal here in visual areas, and the CPP in centroparietal areas. And we found that both of these signals were very strongly modulated by the coherence of the dots. So 0 here is the time at which the coherent motion began. So we were also able to break these signals down by decision outcome. So we have high coherence on the top, low coherence on the bottom. And when we split the SSVMEP signal up into 4 bins based on the response accuracy, you can see it's quite a noisy signal, but here around the peak at around 400 milliseconds, it's very clear that the most accurate responses had the strongest SSVMEP. It's less clear for low coherence, where the signal is very weak. And for response time, when we did the same thing for the response time quantiles, we didn't see as clear a relationship. And we ran statistics at the single trial level, and we found that the SSVMEP did predict response accuracy. So we could do the same thing for the CPP, and again we found that the most accurate responses had the strongest CPP signal, down to the least accurate responses having the weakest. And similarly for the response time quantiles, we found that the fastest responses had the strongest CPP signal. And again, at the single trial level, the CPP was significantly related to response accuracy. So we model behavior with the circular diffusion model, and this is just the results from one example participant. So we have on the left here the marginal distribution, so the fits to the distributions of response error and response times. And on the right here is the quantile by quantile plots, so the joint distributions of response times and accuracy. So we have error quantiles on the x-axis and response time quantiles on the y-axis. And you can see a kind of slow error pattern here. So we have the most accurate responses are also the fastest. We were also able to fit the errors in response time as they varied across stimulus direction. So these changes in error and response time across direction were fit using those drift rate biases that I mentioned earlier. And so then we were able to take those model estimated directional drift rates and test their relationship with the EEG signals. So we found that the directional drift rate was a significant predictor of the CPP, but not the SSVMEP. So this suggests that while directional biases may be reflected in the neural processes of evidence accumulation, the SSVMEP, the sensory level signal, reflects more trial-to-trial variations in accuracy that aren't related to those directional biases. So thank you very much for listening, and a huge thanks to my co-authors and to our funding sources.